How's it going, everyone? Welcome to the fourth part of networks and graphs. Today we're going to have a look at trees and their applications. So there are many applications where only a part of a network is required as a solution to a problem. This section looks at many different problems involving subgraphs and trees, and so we're leading on to more definitions to add to your glossary. So the first one is graphs and subgraphs. So until now, we have used the term network to refer to a collection of vertices and edges, and this network is called a graph. In practice, however, a graph should have at least two vertices and one edge. All or part of this graph can be considered as a subgraph. So a subgraph basically means we use all of the original graph or just parts of it. So last video we had a look at this network here. So we've got 1, 2, 3, 4, and 5. And the entire network can be considered as a graph. So the entire network is a graph. However, the path in which indicated in pink is what's called a subgraph. And we had a look at that in the Hamiltonian paths. So the next definition is called a tree. So a tree is a connected subgraph which cannot contain any loops, parallel edges, or cycles. So going back, the one in pink is a subgraph, but it is actually also what's called a tree. So if I redrew that, this would be a tree. Okay, it's a subgraph because it's just part of the original network. However, it is a tree because it has no loops, has no parallel edges, and has no cycles. So looking at these figures as shown, determine whether each of these is a tree or not. Explain why or why not. So pause the video and have a go. Determine what ones are trees, which ones aren't, and why. So once you've had a go, the first one here is not a tree. Okay, because we've got a parallel line up on the top there. This one here is a tree because we got no parallel lines, no loops, and um, no cycles. This one here is not a tree because of this situation here. I've got a cycle. Right, I can start at one, end up at that one. And part D is not a tree because I've got a loop down the bottom there. Sometimes it's useful to determine the shortest path between two vertices. As I said before, a postman might want to put all the letters in the street and he wants to do it as quick as he can, so he needs to determine the shortest path between all the vertices. Right, it's no point starting at down one end of the street and going to the very end one and then going back. It's going to take him too long, whereas it's efficient to go along each house in order. Another example, new power lines might need to be installed between connecting towns. The cost of installing power lines might be greater if they need to go over mountains, whereas if they went around the mountains, it might be slightly cheaper to install those power lines. So it's talking about the shortest paths. worked example 16, determine the shortest path between A and F in the figure shown. Knowns are labelled A to G, and distance in meters between them are labelled in blue. So I'm starting at A and I want to get to F, and I want the shortest there, A, and I want to end up at F. So from A, well, I have to go to C, and that's worth 5. The distance is 5. Now the next one, all right, let's go to D, and that has a distance of 4. And then from D, I might want to go to straight to F, which has a distance of 13. So adding them up, 4 plus 5 is 9 plus 13. So the distance is 22. So is there a quicker way to get there? Alright, well again I have to start at A and go to C. So 5, I have to go to 5. Now I might want to go to E, straight to E instead, which is A, 8. So 5 and 8, so that's 13. And then from E I can go to F, which is 6. So 13 and 6, so that's 19. So that's already shorter than my first attempt. Alright, so this is the better option. Now I can check other options. I can go A to C to D, then to E, and then to F. I wouldn't want to go to B at all, because that would be pointless, and it would be pointless going to G as well. So there's different options, but in this case, this is actually going to be the quickest way to get there. Again, like our Euler formula, Euler circuit formula, we've got a situation where we can find the shortest path algorithm. So again, sometimes it's difficult to list all the paths between a starting and an ending vertex, so we can use an algorithm to guarantee the shortest path. So step 1, from the starting vertex, find the shortest path to all other directly connected vertices. So start at A, what's the quickest way to get to the next or the closest part? Step 2, choose a vertex directly connected to those in S and find the shortest path to the connecting vertex. Generally, if there is one possible path for each degree of V, although some obvious paths may be eliminated immediately. Add the new vertex V to the list and repeat steps 2 to 3 until we find the vertex that we want. Alright, let's go through it. So, step 1 says, from the starting vertex, find the shortest path to all other directly connected vertices. So, find the shortest path from vertex 1 to 9. So, I want to start from 1 and I want to get to 9. So the first thing says, from the starting vertex, find the shortest path to all the other ones. So I've either got 4, 8 or 6. So in this case, I want to go to 2. So from 1, I go to 2, and that has 4 as the weight. Okay, sorry, I'm just going to make up something slightly different. So we've got a table, so we've got from, to, via, and the distance. So I'm always going to start from 1. So starting from 1, and we just had a look at from going from 1 to 2. So from 1 to 2 directly, our distance was 4. I can go from 1 to 3, and I can go via 2. So if I go from 1 to 2, and then I can go from 2 to 3, that's actually a 7 distance. Rather than going from 1 to 3 directly, because going from 1 to 3 directly was 8. So if I wanted to instead go from 1 to 3, it would be better to go via 2, because that's 7. And if I went from 1 to 4 directly, that was a 6. So my subset, or S, it's actually better to go from 1 to 3 via 2. So I go 1, 2, and then to 3. Step 2 of the algorithm for the vertex connected directly to one in S. So step 2, choose a vertex V directly connected to those in S and find the shortest path to the starting vertex. So selecting vertex 5. Oh, hang on, I missed one. Because we got 1, 2, 3, and 4. So 1, 2, 3, and 4. So the next one is 5. So selecting a vertex 5, which is over here, which is the next one in line. So from 1 to 5, how can I go from 1 to 5? And I want to go via 3. So when you said 1 to 2, 3, then I can go 3 to 5. So via 3. If I went through 3, we had 7. It was the better option. So we went 1, 2, 3, and then to 5. So 7 and 7 make 14. I can go from 1 to 5 via 4. 6 and 9. Is 15. So it's actually better to go this way here. So now my S is 1, 2, 3, 4, and 5. So the next one in line is vertex 6. So vertex 6, I can go from 1 to 6 by number 2. So 1 to 2 to 6, 4, 7 is 11. I can go from 1 to 6 via 3. And I said I want to go, if I go to 3, I need to go this way. So 1 to 2 to 3. So 4, 7 plus 3 is 10. 1 to 6, and I might go through 7. So 1 to 6, but I might go through 7 instead, because we can go from 1 to 2 to 3, and then from 3 to 7. So 4, 7 plus 9 plus 2 is 18. So I'm going 1 to 2, 2 to 3, 3 to 7, 7 to 6. So the shortest path there was this one here. The next vertex in line is 7. So I start from running out of room. Okay, so from 1, and we're looking at 7. So 1 to 7, and I'm going through 6. So 1 to 7, I said before, going from 1 to 6 was 10, was my shortest path. And from 6 to 7 was 2, so that's 12. I can go from 1 to 7 via 3, so 1 to 2, 2 to 3 to 7, so 7 and 9 was 16. I can go from 1 to 7 via 5, 1 to 7 via 5, and I said the quickest way to get there was 14, so going from 4 to 2, 2 to 3, 3 to 5 is 14, plus 4, so 18. So my subset is 1, 2, 3, 4, 5, 6, and 7 now. Next one in line is 8. So I can go from 1 to 8 via 6. So 1 to 3 was 1 to 2 to 3, 3 to 6, which is 10, plus 5, which gives me 15. The other option is I can go 1 to 8 via 7. So 1 to 3, so 1, 2, 3, 3 to 5, no, sorry, 3 to 7 was 12, plus 4 was 16. So now we've got 1, 2, 3, 4, 5, 6, 7, now 8. So our last one was 9, which we want to get to. So I can go from 1 to 9 via 8. And we said that was 15. And plus 3, so that's 18. The other option is I can go from 1 to 9 via 7. And I said 1 to 7 was 12. 12 plus 2 from 2 to 7 to 9, so that's 14. And I could go from 1 to 9 via 5, and 5 was 14. To get to 5 plus 12 gives me 26, so I definitely don't want to go that way. So now I've got 1 to 9. Okay, so now to work out the best possible part. So I said 1 to 9, sorry, 1 to 9, it was better to go through 7. And then from 1 to 7, it was better to go via 6. So 1 to 7 was best to go via 6. 1 to 6 was best to go via 3. 1 to 3 was best via 2. 1 to 3 was best, and 1 to 2, well, that was simple. So 1 to 2 is the best stop. 1, 2 to 3, then from 3 to 6, 6 to 7, and 7 to 9. So the total distance, if we work it out, 1 to 2 was 4, 2 to 3 was 3, 3 to 6 was 3, 6 to 7 was 2, and 7 to 9 was 2. So the total distance, if we add all those up, we get 14. So pretty messy and complicated. It will take a bit of working out to get through those. We'll do some practice of those. The next thing we're going to look at is what's called spanning trees. So in the network shown, the vertices represent school buildings and the edges represent footpaths. So over here we've got a couple of different school buildings and we've got different paths that we can make. And the school council decided to cover some of the footpaths so that students can access any building during rainy weather without getting wet. 3 possible trees which would accomplish this are shown in the figures. So I've got 1, 2, 3 different ways I can do that. So each of these trees included all the vertices of the original network. And these when we do that, it's called spanning trees because of this property, because we use all the vertices in the network. In practice, the school would like to make the total distance covered as small as possible in order to minimize cost. In this case, they would have a minimum spanning tree. So can you determine which of these figures is the minimum spanning tree? So again, another algorithm. So we've got lots of these now, and this one for determining minimum spanning trees is called Prim's algorithm. So we've got choose the edge in the network which has the smallest value. If 2 or more edges are the smallest, choose any of these. The next one, inspect the 2 vertices included so far and select the smallest edge leading from either vertex. Again, if there is a tie, arbitrarily choose any one. Inspect all vertices included so far and select the smallest edge leading from any included vertex. If there is a tie, again choose either of them. Repeat step 3 until all vertices are included. Example 18. So we've got determine the minimum spanning tree for the network representing the footpaths. So we're going to start at A. So starting from A, step 1, find the edge with the smallest distance. This can be done by listing all the edges and choosing the smallest. Well, from A, that one there is going to be the smallest edge. So we want to start there. Inspect A and B and find the shortest edge connecting one of these to a third vertex. So A and B, I can either go A to E, which is 62, or from B, I can go B to D, which is 75. So I actually want this one here. So I actually want A to E. Okay. A to C, I don't want A to C because that's 100. Right, so just from either of those vertices, I've got 100, 62, or 75. This one's the better option. So I actually want A to E. Inspect elements, the vertices A, B, and E now. So A, B, and E. From A, again, I can either go 100, 62, or 32. So A to C was 100, E to C was 45, E to D is 50, and B to D is 75. I want this one because it's the shortest. The next one, we continue until all vertices have been connected. In this case, only D remains. So looking at D, I've got B to D, which is 75. I've got E to D, which is 50. And I've got C to D, which is 78. So I actually want this one here. Since all the vertices have been connected, this is the minimum standing tree. So I want to start with A and B. A and B, which was 32. I want A and E, which was 62. I want E and C, which was 45. And I also want E and D, which was 50. So my minimum spanning tree would look like this. So we've got B, A, E, A to B, A to E, E to C, and we've also got E to D. So it would look like that. So that's my minimum spanning tree, and here is my numbers. Okay, so that's using Prim's algorithm. Sometimes it might be worth looking at the maximum spanning tree. Basically the same thing, except we look at the largest edges instead of the smallest. So example 19, got a figure representing telephone network connecting 6 towns, A to F. The number of edges represent the capacity of the telephone connection between the towns connected. That is the maximum number of calls that can be made at the same time. So a telephone engineer wishes to determine the maximum capacity for the systems of... Okay, so using Prim's algorithm again, just by inspection, look for, in this case we want the maximum. So the maximum number is A to E by the looks of it. So we're going to start with A to E because that was the maximum, which is 66. Alright, looking at A, I can have A to B, or I can have A to B, which was 58, A to C, which is 56. I can have A to F, which is 54, and A to E, we've already got A to E, sorry. The other option is I've got E, and that can go to B, which is 49. I can go from E to F, which is 62. And I can also go from E to D, which is 53. So the highest number in there is going to be E and F. There's my first one, there's my second one. So I've got A to E, E and F so far. Now I can go A to B, which is 58, A and C, which is 56, F to B, which is 35, F to C, which is 60, F to D is 41, E to D, which is 53. So in this case, here's my second option, F to C is the best one for the maximum. Now I've got A, B, A, F, E, and C. So if I go from A to B, that was 58. Or I can go A to C, which was 56. Don't want to go to F, already got E. Move on to E, I can go from E to B, which was 49. I already got F, or I can go to D, which was 53. From F, I can go F to B, which was 35. F to D, which was 41. That's no good. From C, I can go to B, which is 45, and from C to D, which was 37. So in this case, A to B is going to be the best one there. So I do want that one now. And last one is D. So all the vertices connecting to D. So I don't want to go to C, B to D, which is looks like a 58. I can't go from A to D. E to D was 53. F to D was 41. And C to D was 37. So I actually want that one there. So final one is that one down there. So there's my maximum spanning tree now. So maximum capacity would be 66 plus 62, I think that was, plus 60, 58, 58. So if I add them all together, it equals 304. Dijkstra's algorithm. Another method for determining the shortest path between given vertex and each other vertices is given by Dijkstra's algorithm. So an effective way to use this algorithm is using a tabular method, and we're going to have a look at that in example 20. So determine the shortest path from A to E where the distances are in kilometers using Dijkstra's algorithm. So like a matrix, we're going to make well, similar, but it's a tab form. So we've got A, B, C, D, and E. A, B, C, D, and E. So construct the table representing the network. In the middle, we're going to label our the weights of each path. So from A to A, there's nothing. B to B, there's nothing. C to C, so we shouldn't have any loops. A to B was 16. A to C is 8. A to D, there's no direct pathway, and A to E, there's no direct pathway. So from B to A was 16. B to C is 9. B to D is 10. B to E is 15. So just filling out the table. Okay, and just leave those blank. That doesn't have a connection between them. So the next step is starting at E, place a 0 above it. So starting at E, because that's where we want to end up. So place a 0 above it. And the options are B, which is 15, and D, which is 14. So we've got 14 and 15. So B to D, which was 14, or we've got 15 over there. So in the spots, that's underneath it, yep, so that's where they come from. Paths, next step, go to the shortest distance, which in this case was D, and go down vertically. So we want D, and we go down. And the next one is a 10. So add 14 and 10, which equals 24. And this is greater than 15 already above B, so we don't want that choice because we've got 14, 15, 14 and 10, which is 24, which is more than that. So we don't want that one. The next option down is 6, which is C. 14 and 6, which is 20. Since there's nothing above C, we add the 20 in there. And we started at E, so we don't want to go back. Okay, now E and D are done. The next lowest is B. So next lowest was B at 15. So directly down is A, which is 16. Add 15 and 16 is 31. And because we don't have anything above A, we write 31. Next lowest is C, which is 9. 15 and 9 is 24. This is greater than C, so we don't want that one. We've already done D, and we've already been to E. Now E, D, and B are done. The next lowest is C. So next lowest is, oops, we've already done that one. So next one is C. Going down is 8 to A, so 20 and 8 is 28. And since this is lower than 31, we replace it with the 28. And we've already been to B, and we've already done D. So the shortest distance from A to E is then the number above E, which is, in this case, the 28. So the shortest distance from A to E is 28. Now that doesn't specifically give us the path, but it does give us the distance. So it's the shortest path. So that's the last part of chapter 9. So that's trees and their applications. Have a go at the questions. We're going to have a lot of practice of using those algorithms because they do take some time to understand. Thanks for watching.